Hello! Welcome back to Stat 3050. This is the end, my friends. This is the end of the class, not of times. So no need to get too worked up. So this video is going to be answering sort of all the most frequent, most common questions I saw get asked. But there's also a few things that I want to sort of wrap up too in this video. So we're tying up some loose ends. So let's get into it. The biggest, most frequent question was sort of when to use what test. A lot of this class covers many things. T-tests and ANOVA are super important to learn, but we did that way before spring break, so it's like totally fine that that's sort of, in the back of your mind. Regression is more or less sort of a stronger test anyway, or a stronger tool to use. But there are certain situations where t-tests are the test that you want to use. Same thing with ANOVA, same thing with regression. So I've tried to make sort of a general sort of flowchart kind of situation here that should help sort of answer your question and kind of organize all of these different tests and tools that we've learned. Okay, so what it really boils down to is what your question is. Okay, so I've got a bunch of different questions here, generalized, of course, and I'm just going to go over them sort of quickly here. But the most simple question, I think, is group A, some group, whatever, statistically different from some known mean? Okay, and if that is your question, then the one sample t-test is going to be your friend here. So what does that look like? Let's go back in time and just sort of recall that when we're doing t-tests, what we're doing is essentially comparing two groups with each other and seeing how much they overlap, right? So this area here, this kind of green area, is how much these two curves overlap, these two distributions, and that is our p-value, right? And the further apart those two distributions are, then the smaller the p-value is. Okay, so in this situation, let's say that our blue curve is our data that we've collected. Okay, we'll just say that's x bar for now. So that's the mean, right? The blue represents the whole distribution. And then the orange curve here represents the simulated distribution of some known mean. Okay, so depending on how many observations we collected, the simulated data set, or the simulated distribution that we're working with is also going to, have that same kind of shape, right? Depending on how many other observations we had in our comparison group. Okay, so whatever. That sort of math, again, is not super important. Again, we'll get into the math because a few of you asked why we haven't really gone over a lot of the mathy stuff in this class. I'll tell you why in a little bit, but not now. But this tends to be kind of complicated when you get into all the different what distributions look like at different observation counts and different distribution types, blah 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 blah. So instead, I'll just give you a quick example of what this would be like. So with a one sample t-test, that's just comparing one group to a known mean, okay? And the question would look something like, is the GPA of Stat 3050 students statistically different than the mean GPA of University of Wyoming students, okay? So what this is saying is we can collect all of the GPAs of the Stat 3050 students fairly easily, right? There's like 50 of y'all. That's not, a huge number that is like onerous to collect or whatever, but it is onerous to collect 10,000 other GPAs of all the University of Wyoming students. However, we know that maybe the mean of the GPA of UW, making it up, of course, but we'll just say that mu here, equals 3.0. Okay, that's our known mean. And then we just collect the GPA of Stat 3050 students and then conduct a one sample t-test. Okay, so that's sort of the process here. Find the mean GPA of UW, which we found, quote unquote found. I made up. And then collect the GPAs of Stat 3050 students, right? So that's going to be 50 things, right? Or however many students there are in the class. And then we'll conduct the one sample t-test. So the code looks like this, t.test, remember. And then x equals, this is what I have called the data set. Okay, so stat3050.gpa, $ to look inside the data frame, and then the one variable that's in there is GPA. Okay, and then mu equals 3.0. If you were to leave that blank or not even type it at all, right, it will default to 0. Mu equals 0, right? We don't want that. We want to shift it over just a couple, over to 3, to see if our mean GPA of the University of Wyoming students is different than the GPA of Stat 3050 students. Okay, so you run all that, and then you get the one sample t-test. The t-stat here, remember, is just how far the two distributions are from each other, right? So this sort of area here, that's the t-stat. And then the area underneath the two curves that are shared is the p-value. And we see that right here. Okay, so less than 1% of the two curves overlap, right? So that means that there's pretty significant evidence that they are different, we would say. So then we get the 95% confidence interval, and then we get the mean of x. So that's fine. So we would come back over here to the conclusion, take what we want out of the results and say, based on the one sample t-test, we have significant evidence that the GPA of Stat 3050 students, is statistically different than the mean of UW, right? And then we would say the p-value. In this case, it's kind of convention just to do less than either 0.05 or 0.01, depending on how small it is. In this case, it's 0.001. So we just say it's less than 0.01. That's fine. And then we have a little interpretive sentence saying sort of the mean GPA of Stat 3050 students is 3.57, while the mean of UW is 3.0. Okay. So that's pretty much that, right? Nothing too crazy. How often will you do a one sample t-test? Probably not that often. It doesn't really, it's a decent question to ask. Sort of, you collect one column of data and compare it to some known mean. Doesn't really happen that often, but still, good to know about. What is more common, though, is having two different groups, okay? So that's sort of the next question. Is there a difference between Group A and Group B? The next question is, does Group A contain the same people as Group B, just measured at two different times? If the answer is yes, then a paired t-test is the tool that you want to use to figure out the difference between pre and post intervention, for example. If that is not the case, if you have two groups that have two different people, right, two different groups of people, then you want to do an independent t-test or two-sample t-test. Two-sample is sort of not a misnomer, but it is kind of confusing because a paired t-test also has two samples. It's just containing the same group of people both times. So independent t-test is a little bit of a more accurate way to describe what the test is doing. But again, you'll see it both ways, and it's fine both ways too. So let's look at the paired t-test example, and then we'll move on to the independent t-test. So oftentimes, a paired research design will be sort of a pre and post intervention type of thing. Okay. So for example, how does an 8-month marathon training program affect weight? Okay, decent question. Very realistic, right? We see this sort of stuff all the time. So the process is, first you want to find people who are willing to train for 8 months for a marathon. It's kind of a long time to train. Unless it's one of those couch to marathon for 5K or whatever things. Okay, anyway, getting off track. Find people who are willing, and then collect weight or collect your data or whatever before you do the intervention. Okay, So you bring all these people in, weigh them up, record that data, and then you conduct the intervention, which in this case is a marathon training program. You wait 8 months as they're doing this training program. You come back and then collect the weight after they have finished, after they have completed their training program. And then you run the paired t-test and see whatever you get. Okay, so again, the code t.test, pretty much always the code you'll use for t-tests. Just in this case, we've got x and y, where x is, depending on the order, however you want the algebra to kind of work out, x is going to be your pre and y is going to be your post. You could flip it if the signs are negative or if it doesn't make sense that the signs are negative, whatever. And then you just want to make sure that you have the paired equals true here, because the default is not paired equals true. The default is paired equals false. So you want to make sure that you get that in there correctly. So the paired equals true, that's just part of the study design, right? So you'll have paired data. You'll know that you have paired data pretty much always. If it's the same group of people, pre and post, paired data. If it's two different groups of people, unpaired, right? So you'll know when to run a paired t-test. So then you run that code, whatever, and you get the results here, t-value, how far away the two distributions are from each other, essentially. The p-value here, way low, right? It's way below 0.05. It's way below 0.001. In fact, it's 4.6 times 10 to the negative 13. So that's like pretty close to zero, right? Effectively zero, almost. And then you get a 95% confidence interval for the difference in the means, right? And then you get the mean of the differences, right here. So that's fine. That's good. So what we would say is, based on the paired t-test, we have significant evidence that the pre-marathon training program weight is statistically different than the post-training weight. Okay. We say the p-value is less than 0.01 because it is. It's way less than 0.01, but that's the convention. And then we would say that individuals lost 16.9 pounds on average, right? And that's that, right? So you have this paired data, pre and post intervention, run the paired t-test, and you're set, and you're good. And that's that, okay, for this pre and post kind of situation. However, you'll also see like pre-survey, post-survey measurements, right? And then you would use a paired t-test for that, okay? So pre-survey, post-survey can be many things. In psychology, you'll see that as sort of how do you feel about a class before taking it, and how do you feel about the class after taking it, for instance. It could be many things. It could be emotions, pre and post, reading some book or doing some therapy or something, right? That's an example of pre-survey, post-survey. You can also do a situation where it's like surveying land for some sort of measurement. That's the example that I have here. The reason is, in biological data, it's pretty easy to do these t-tests. In psychology, sociology, paired t-tests for surveys, it's a legitimate way of doing it. They also have other quote-unquote non-parametric tests. We didn't touch on them because that's not really the point of this class. That's more for a psych stat class. But it's doing the same thing, essentially. So, anyway, sort of a tangent there. In this case, we have a question, and it is, how does shrub density change after a controlled burn 1 year later? So what does that look like? What does the process look like? So first you want to find the survey site, whatever. Either you go out and sample it, or you already know where you're going to go. And then you measure shrub density, and then you burn it. You burn it all, and then you wait some period of time, a year in this case, and then you go back and then measure that same shrub density again, right, of the same species, right? And then you conduct the paired t-test. So I'm not a fire ecologist, but usually, burns are done to kind of clear out some plot of land, and then the native shrubs and grasses can grow back, and maybe the invasive species are gone, right? Sort of choking out the native stuff. So anyway, that's sort of the idea with this example, is that you expect for the shrub density to go up, maybe, right? So that's why I have it here. I have the X and the Y flipped, right? So in the last one, we expected to see a drop in weight. In this case, we're expecting to see an increase in density, right? Again, I had to do this twice just to make sure that I got the signs right. Again, it's just flipping around 2 lines of code, nothing too crazy. And then you get the results, pair t-test, you get the t-value. Again, not super important to report that, but the p-value is what we care about. At least that's the convention to care about. And then you get the mean of the differences down here. Uh-oh. Oh, no. Keep. No. Oh, Lord. That's all right. We're coming back. And then I'm not going to edit this out. Oh, man. Editing these videos, truthfully, takes such a long time. Okay, so sorry about that. Now, okay, so we've got the results, p-value, mean of the differences. Booyah, we're set. And then we just come over here to the conclusion and say something along the lines of, based on the paired t-test, we have significant evidence that the pre-burn shrub density is statistically different from the post-burn shrub density. And then you could do the math yourself. You could just report the mean of the differences, whatever. And you would just say shrub density increased by 15% on average, right? If you cared about the directionality of it and wanted to make the p-value even smaller, you could just cut the p-value in half and say that you are that much more certain that the density increased. Again, that's getting into the one-tailed, two-tailed tests. It's not... If you don't know what sort of difference you'll see, then just do the two-tailed and you're good, right? And that's that. Okay. So paired data, you'll know you'll have paired data based on the design of the study, if it's got the same people or if it's got the same place or whatever. That's going to be paired, right? Just to sort of start off with that. Okay. What if you have 2 separate groups that you want to compare? Okay, so instead of having the same people in group A and group B, you're going to have 2 different types of people, right? In group A and group B, right? So in this case, right, an example would maybe be, how does resting heart rate differ between cyclists and non-cyclists? Okay, good question, genuine question, right? Something you'll see frequently in your reading, in your literature. But the idea here is that you want to find willing participants that match some requisite criteria, whatever. That's just saying that, you're not going to have a ton of old people comparing, like a ton of old non-cyclists compared to, a bunch of young cyclists, right? You want to have sort of controlling measures like that. You want to make sure everyone's the same age, maybe, or like the same weight or whatever, right? That's sort of up to you how you design the study, and not so much, worrying on the statistics side of things. So just sort of keeping that in mind, right? You want to make sure everyone's just about the same, and one big thing is different. In this case, cyclists versus non-cyclists. Then you collect the resting heart rate from each group, right? Doesn't really matter when you do it. As far as like with a paired design, you want to make sure that you collect everyone right around the same time. In this case, it doesn't really matter. The one thing that you're looking at is this big difference between cyclists and non-cyclists. And then you conduct the 2 sample t-test, and then you're set, right? So X and Y, cyclist, non-cyclist, there the order doesn't really matter, unless you're trying to, from a storytelling point of view. Sure, it does. It's often easier to understand, differences when they're positive values than negative, but, whatever. Here, I've left it a negative just so we can see that cyclists, in this case, have a much lower resting heart rate than non-cyclists. And we see that here. Whoa. Sorry. That's right. So we see that here with the p-value, that we have significant evidence that they are different, at least. And then the mean of X here is 50.05. the mean of y is 71.39, right? We know that x is the cyclists and the y is the non-cyclists, so they're on average about 21 beats per minute different, right? Cyclists have on average 20 beats per minute lower resting heart rate than non-cyclists. So coming over here to the conclusion, based on the independent t-test or two-sample t-test, we have significant evidence that the resting heart rates between cyclists and non-cyclists are statistically different, p-value less than 0.01. So that's fine. That's good. And then you would report the mean of both groups. So the mean of the cyclist is 50.1. Mean of the non-cyclist is 71.4. Okay. You can also report the difference between the two, but just be careful with that because we're not really working with differences. We're just looking at how the two distributions differ. Okay. So I think they're testing the tornado sirens right now. It's so annoying. Sorry if you hear that. The world is not ending right now. It's just a test. So when it really ends, we all don't freak out. Okay. So with the paired t-test, we are specifically looking at the difference between pre and post, right? The difference, the literal mathematical difference, right? X minus y. In this case, we're just sort of looking at how the two distributions are different. And we would say that one is bigger than the other. Okay. You can still report the difference in the two means. You just got to be careful and make sure that you really say that it's an independent t-test and not a paired t-test. Okay. So that's the group A versus group B comparison. It's the most appropriate to use a t-test when you have two groups measuring the same thing and you just want to see what the difference is between those two groups or how they are different. Okay. What happens when you have 3 groups or 4 groups or however many? Well, then you want to use an ANOVA, right? You're still looking at one single outcome, right? But you've got everything separated into maybe more than 2 groups, right? So you do the ANOVA, and then after that, you actually have to figure out what groups are different from each other, okay? We have 3 different ways of doing that. Bonferroni corrections, Tukey, honest significant differences, and then false discovery rate. 3 totally valid methods to use. We all know that I have a favorite, and it's Tukey. But again, depending on the context of the analysis that you're doing, it might make sense to do a different one. Okay, so Bonferroni, just for a refresher, it's super conservative, right? But the differences that you do see, the p-values that are statistically different or statistically significant, are certain to be true, right? We're leaving very little up to chance when we use Bonferroni stuff. Put technically. Okay, and then the Tukey, it's a little bit more liberal, but it's not too lax, right? It's pretty moderate. I like it because it gives you more information initially. You kind of have to do some digging with the Bonferroni and the FDR. But it's a decent place to look when you're just not really sure maybe what you're working with or what you're expecting to see, or if you're just doing kind of a generalized exploratory study, for instance. So that's all good. And then the false discovery rate, it's pretty lax, which might be good for when you're just looking for general trends, right? Or general differences. And then just sort of helping you develop maybe different hypotheses for future studies, right? So that's all good. That's all fine. What does this look like, though? Because we sort of are, like what I said earlier, there's a lot of overlap between these tests. Can you use an ANOVA on just 2 groups? Of course you can. That is way overkill, though. Right, that's like, what is that like? What is that like? I don't want to say bringing a gun to a knife fight, but I guess it kind of is like that. Where sure it works, but you're gonna be questioned as to why you did it, and it also takes a little bit more work too to use this tool for sort of a simpler case, right? Still, you totally can do it, in fact, with 2 groups, it doesn't matter what correction method you use. Because you're not correcting for anything, because you're still just doing 2 comparisons, right? You're doing the minimum amount of comparisons that you can do. Okay, so again, let's look at an example for this. Wait, let's not look. There's another question that came up, and I want to make sure that we get it. So, why do we even do post-hoc comparison tests versus just a bunch of t-tests, right? Well, doing a bunch of t-tests would take a ton of time, right? Tons and tons of time. But the biggest reason is because the more group comparisons that you make, you are more likely to make a false discovery, right? You are more likely to say that something happened when it really didn't happen. And that's not, your fault, not specifically you, but it is just the world that we live in, right? Mistakes happen, and the more things you do, the more likely you are to make a mistake eventually, right? So, the more comparisons you make, you have to correct for that probability of making a false discovery. So, post-hoc comparison tests do account for that, but doing a bunch of t-tests don't, right? Because when you're doing 2 t-tests, not 2 t-tests. When you're doing t-tests, you're only comparing 2 groups, and it doesn't even consider that you've made other group comparisons too. It's treating everything independently, which you don't want in the case of multiple comparisons. Again, said earlier, writing out code for t-tests is going to be super cumbersome if you get a ton of comparisons to make, and you're more likely to leave something out too, just as a typo or something. And then the biggest thing, we've learned that statistics is super subjective. So these post-hoc comparison tests, the Bonferroni or Tukey or FDR, there's tons and tons of other ones too that we haven't gone over because they all do about the same thing. But it does allow you to be a little bit more subjective, right? Depending on what you believe in, you can kind of apply that to what test you decide to use. Okay, so that's sort of the 3 big points here. The biggest one, the more comparisons you make, the more likely you are to make a false discovery. And then after that, t-tests can be super cumbersome. And then if you have certain thoughts about how something should be, you can sort of apply that to your analysis. So now let's look at an example. So you got multiple group comparisons here. The question is, how do departments, we have 4 departments, stats, engineering, physics, and English, differ in GPA? Okay. So the idea is to collect all your data, right? Doesn't matter how you do it, but you've got data, whatever. And then you analyze that with an ANOVA. And remember that ANOVAs, the question that they answer is there a difference at least once, right? Is there at least one difference between the groups, right? And then the p-value that you get there is saying, yes or no. If it's less than 0.05, then it says, yes, at least one of the groups is different than another group, right? It doesn't tell you anything more than that. So then you have to do the post-hoc correction. Depending on your opinions on that, will vary which test you use. But we see down here in the code, that I use Tukey because I like it for many reasons. So this right here, this is your initial model output. That's supposed to be an arrow. Good Lord. That's your model output. That's your ANOVA in general. And then you get the p-value saying, is there a difference at least once? Yes, there is. The p-value is less than 0.05. And then you have enough evidence to do a post-hoc comparison. And then that just spits out all the different combinations, the difference between those combinations, and then the p-value. And we see here that all of the groups are different from one another, right? So English is different than stats. Physics is different than stats. English is different than stats. Oh gosh, engineering is different than stats. Whatever. Physics is different than engineering. English is different than engineering. English is different than physics, right? And we have the p-values backing that up. Now, since we have gotten into regression, 2 things. First, since we've gotten into regression, we can use a little bit more specific language here. So going over here to the conclusion, the ANOVA showed a significant main effect of department on GPA. You report the F value, again, that's totally convention. And then the p-value, again, that is more important, I think, to report. And then after that, you would report, whatever the post-hoc comparison test was, right? Whatever those results were. Again, with the p-values and the difference if you want. The second thing is that we worked with an example where we did regression with just this one categorical predictor, and the outcome being, whatever it was. I think it was the movie. It was in one of the labs, or in one. Maybe it was the one of the notes. But it was like a movie. How movie genre affects rating or something like that. We could have done an ANOVA, and in this example, we could have done regression, right? However, ANOVA is a bit more appropriate to use here. One, convention, right? Totally subjective. But the second thing is that it does sort of account a little bit better for the multiple comparisons. Doing regression doesn't really do that. You still do get the same output, and if you're curious, you can do this with regression. You'll get the difference here, this DIFF column, would actually be your slope coefficients, funnily enough. However, the confidence bound here is different in the Tukey HSD and what you would get in regression, because it's correcting, right? It's correcting for multiple comparisons. And then the p-value for that would be slightly different too. Not so much in this case because they're all super low anyway. Again, nothing would ever be totally zero, but we would just say they're less than 0.01. But everything changes a little bit when you do it in regression. In this case, if you just have groups, and nothing else, use an ANOVA. And that's sort of the outcome is some continuous thing. Okay, so that's all good. That's all fine. Next question. Let me take a sip of my coffee here. Okay, I'm ready. I'm revived. Talking so much just really dries you out. Okay, anyway. What's the relationship between something, and another thing? Okay. I've tried to put this as general as possible, but how many things do you have is the next question, right? So again, we're only looking at one outcome, right? One y variable, but we can have at least one predictor, and then we can have more than that, right? So if you just have one predictor, if you just have one thing, then that's going to be simple linear regression, right? Beta naught plus beta 1 x1 equals y, right? Or y is a function of x in some way. If you have more than one predictor, then that's going to be multiple linear regression, right? So let me actually just write this out. Y equals beta naught plus beta 1 x1, and that's it. For multiple linear regression, you get y equals beta naught plus beta 1 x1 plus, and then ... all the way out to beta k x k, right? So you can have a ton, right? You can have as many as you want. Another question that came up is if you have like 20 variables that you collected, or a data set that you're working with just has 20 variables in it, what's the best way of figuring out what you should include? Well, you can use the subsets function, right? So the leaps package, you can do the reg subsets and then the subsets function. That will mathematically tell you, the quote-unquote best one. But you can also just go in and say, okay, which ones make sense? Which ones do I want to include? Depending on your purpose, right? So it might make sense to include all 20, especially if they all turn out to be statistically significantly statistically significant. Sorry, I'm getting the language kind of confused here. Sorry. But again, you can just, if all the p-values are below 0.05, just keep them all, If prediction is your goal, if prediction is your goal, and they all are statistically significant, and the intercept is statistically significant, then keep them all, right? You just have a really decent model. Again, you want to make sure that you don't have like an overfit model, and you want to make sure that all of your predictors are relevant to the outcome. That's sort of the biggest thing there. But if your purpose is just relation, then it might just make sense to include, the biggest 3 contributors to the outcome. You can look at it based on the p-value. You can look at it based on, R squared or BIC or AIC or whatever. It's all depending on your purpose, right? So, okay, so that's the next one. There's another thing too that is still getting a little bit confused, which is fine. But let's talk about. Let me bring up a blank one here. Let me just do this real quick. Sorry, you're seeing the behind the scenes. All right, okay. Sorry. Okay. So you get some model output from regression. Let me do this. Get my pen out. I'm going to use the light blue. So relation. That's when, p is less than 0.05 for the predictor slope coefficients. So for the beta k's, right? And that's it, right? For a relation, you really don't care about where the line intersects. You just care about how the line looks, right? And how it changes when x changes, right? So it could be there, it could be there, it could be here, right? You don't care where it is. You just care that the slope is the slope, right? And we can trust it. So here, we've got some x and some y. We would just say for every 1 unit increase in x, y changes by, some amount, whatever it may be. And that's going to be our slope coefficient that we get. Okay, let me erase all that. And then for prediction, just put P-R-E-D, pred. For prediction, you want P less than 0.05 for the slope coefficients and the intercept. Okay, so you care about where it hits the y-intercept and how the slope of the line behaves generally, okay? So what you're essentially doing here and what the computer would do here is that for prediction, you would just say, okay, my x equals something. You would trace it up and trace it over, and that's that, right? Same thing in the multiple regression world. For every p-value for the slope coefficients that you get, right, regardless of how many you have, if one of them is statistically significant, so let's say, let me erase all this again. I'll write out, let's say that you just have 3. Whoa. Yeah, let's just say that you have 3. Hopefully I don't run out of room. Okay, so that's what your regression equation looks like. This has a p-value of 0.05 or less than 0.05. So does this one, and so does number 3 here. Okay, number 2 doesn't. Okay, so we can use this model for relation for this variable, whatever it may be, and this variable for relation, right? We would say here for beta 2, for x2, we would say there is no relationship between x2 and the outcome, okay? Okay, so that's fine. So relation for these two. But then we also can use the model itself for prediction for beta 1 x1 and beta 3 x3, right? We can't predict any of any new y values based on this beta 2 x2 component, right? This does nothing for us. In fact, for prediction, it would just make sense to kick that out and then see how the p-values change for the beta coefficients of the leftover values, right? Or the leftover variables that we have. So that's the idea with prediction versus relation, right? Relation, we don't care about the intercept for relation. We only care about the p-values for the variables that we have. For prediction, everything needs to be statistically significant. And then if it's not, then just kick it out and wait until you get a model that has all significant values, right? Okay. So that's all good. That's all fine. Oh, boy. Okay, so kind of in the same vein, we talk about residuals a lot. And residuals essentially just tell us how our model is doing, how adequate it is at showing the relationship, at least, between one or more things to some outcome, okay? And so why are they important? Why are they important? Well, let's say that we're working in, it really actually doesn't even matter what dimension we're working in, but let's just keep it in 2 dimensions for now. And let's say that, our regression line looks something like this, and then we have data that looks like this. Okay, so the line is legitimately calculated, but we already see that there's some clumping over in one end and then not in the other, right? So in just these 2 dimensions, the residual plot would actually, let's use a different color. The residual plot would look identical to this, except it's just flipped over. Okay, so it would look like this. This is the residual plot. And then, I'm not going to draw it exactly, but you'd see that it kind of fans outward like that. Okay, so what this is saying is, and we can look at either of them, right? In 2 dimensions, we can look at either of them. And this is, let me actually write this out too. This is this equation. Okay, so we just have one predictor. That's what I mean by 2 dimensions. Sorry. So what this model is doing, right? What this line is doing is saying that, over here, it's going to do a pretty decent job of explaining the relationship between x and y. But the further you go out, the more spread out the points get, the more uncertain you are that that line is doing a decent job, right? And the same thing we see in the residuals, right? Now, that's all the same in the multiple regression world, right? So I'll draw that too. So in multiple regression, we cannot draw a plane, a single plane for the line, right? We have to draw it in like a 3-dimensional space. One of you asked, or maybe a few of you asked, can R plot in multiple dimensions? Yes, it can. There's a few packages out there that are able to make 3D plots. I don't remember them off the top of my head, but they do exist. Again, though, looking at a regression plane rather than a regression line is not very intuitive. So you can do it if you want. Not recommended, at least for the public. So, sorry. Anyway, so you have this residual plot, right? This is the residual versus fitted. And again, in this case, we could just say this is the multiple regression. Looks something like this. Just say beta k, xk. Okay. What this is saying is that the model is doing a decent job, over here, but not doing a great job in this sort of range here. There's a lot of sort of variability the further you go out. So this brings us to our next thing, where you can log transform variables. And one of you brought up a fairly decent point in that, like, when we log transform, aren't we sort of breaking some rules by manipulating the data? Well, no. That's a good question, and definitely good that you're asking that question. But what log transforming does is that it moves the frame of the question from does x and y, do they behave linearly? So there's a fairly kind of predictable amount of change as x increases or as x decreases, and the change in y. Do we see that? When we log transform, what happens there is it's instead of saying does it grow or does it change linearly? It's saying, does it grow or does it change relatively? Okay, so we're put in the world of percentages then. So we're not manipulating the data. We're just saying that, okay, instead of saying as x increases by 1 unit, we would say maybe as x increases by 10%, y changes by this much, right? Because percentages, we know, behave differently at different values, right? So that's sort of the idea with log transforms. And it also turns out that when you log transform, that's sort of the most common. Another person asked, what's the most common what's the most common transformation? That is sort of one of them. That's, I would say, the most common. It turns out that when you log transform something, oftentimes you'll get more spread out data points. And it would look something like that. So even though the data points are more spread out now, the error term or the error component of the model is consistent, right? So more or less, we are consistently wrong, right? We're not overestimating or underestimating more in one place than another, right? We're saying that, the over-under is about the same regardless of where you are in the data. Okay, now, there's a bunch of visual tests that we can do. We look at the residual versus fits. We look at the distribution of the residuals. The two other plots and that 4-in-1 plot, one of y'all asked this, they're still the residuals, right? One of them is the standardized residuals, so it's the same pattern. They're just all positive values instead of negative and positive. And then the other one, depending on what kind of data you have, more or less just kind of shows the overall spread of everything. Again, the most commonly used for the visual inspection are the residuals versus fit, looking at the pattern, or if there is a pattern. And then the QQ plot, which just shows essentially what the distribution looks like. Now, one of you also asked, what does the QQ plot show you? It's fairly unintuitive, but it essentially shows you where each residual data point lies in the theoretical perfect normal distribution. Ugh, it's gross, right? Just plot the histogram of the residuals, and you can see whether or not it looks, decently normal. Okay. A few of you asked, or actually maybe just one person, but I thought it was a good question. Are there more stringent tests we can do to test for normality? There are, but there's one sort of big caveat with this, is that statistics, it's not math. Even though we're sort of using math, it's not math, right? So it's a good idea always to look at the residuals and do a visual test. Some people say it's not good enough. Other people say, it's fine. I think that it is fine, and most people in the stat department do think that it is fine. But when you visually look at the residuals, you as a person, you as a researcher, you as a scientist are saying what you're cool with, and if it's okay that the model is over or underestimating more or less in one spot than another. The second big thing with this is that you just don't want to plug in your residuals into some test and it just tell you some number and you say, okay, it's fine, whatever, and move on, right? You want to make sure that everything is fine because some of these tests are sort of biased to, imperfections. What was that? Oh gosh. I don't know. I don't know what that noise was. You probably didn't even hear it. Sorry. Okay. So, going back, doing just a simple test and saying, oh yeah, it was good because blah, 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 whatever. That's not statistics, right? You want to have at least some, honestly, personality, and subjectiveness to what you're doing. So, with all that being said, here are two tests, that you can use to test normality. The Shapiro-Wilks test. It's pretty easy to use. Both of these are in base R, so you don't have to download anything or install anything. The Shapiro-Wilks test just tells you, whether or not the data is normal based on like an algorithm. And the Kolmogorov-Smirnov normality test, the KS test, tells you the same thing, right? However, here's the big thing. Here is the big thing. With these kind of tests, you want, good Lord, oh my God. You want a p-value of greater than 0.05. Not less than 0.05, but greater than 0.05. So that's the only kind of weird thing about it. If the p-value is less than 0.05, it's saying that the data is non-normal based on this test or whatever. If it's greater than 0.05, then it is normal, quote unquote, right? Again, take these at the grain of salt. They can be sort of sensitive to strange your, looking distributions. If the sample size is small, you might be able to say that, hey, actually, the residuals are normally distributed. It's just a small sample size. This test will tell you that they are not normally distributed. So just keep that in mind. You can do these. I didn't show you them because this is not really, the best way of looking at normal data. But again, you choose how you want to do it. This is a decent way of doing it. Doing the visual test, I think, is better. But again, totally up to you. Taking another sip. Okay. All right. Polynomial terms. When to use them. In simple, quote-unquote, simple linear regression, it should be fairly obvious. It should look something like this, where you have the data, some x and some y. And if the data look like this, right, that's fairly evident of there being some sort of polynomial, in this case, sort of a quadratic term. That's good. If you were to draw a line, just a straight line through it, it would look like not good, right? It would look like that, right? The residuals would also look really bad. But if you were to draw a polynomial line, more or less sort of a quadratic situation, it would look like this. Wow, cool. My bad. And that regression equation would look like beta naught plus beta 1 x1, and then beta 2 x1 squared, right? Because it's the same thing. It's the same variable there, just twice. So that's all good. That's all fine. That's sort of the most simple way of seeing it, right? If you have this fairly evident curvature. Again, that's for the quadratic side. If you had something that looked like this, where it goes out like this and then back up again and then back over, that might be more or less sort of a cubic term, maybe, where it goes like that. Maybe even a fourth order polynomial. Oof, right? It gets really out there really fast. Depending on the context, right, you might want to model it as complicated as possible, so you can accurately describe, the line, the behavior of the line as time goes on, right, or as x increases. However, if that curvature really isn't there, if that's not all the story, right, modeling it as a polynomial regression equation, you might be overfitting the model, kind of overcomplicating it. Again, totally depends on the context, right? If you're trying to predict something and you're trying to get it spot on, and it does look like this, right? And if you were to go collect more data and it does sort of start to fit around this line, then maybe it makes sense to do a third order or fourth order polynomial term. Quadratic terms are a little bit more natural, I think, especially when you're looking in engineering, and when you're looking in biology too. Crop yield is a big one that has that sort of quadratic that sort of behavior, at least. That's sort of the big thing. Now, in multiple regression, it's a little bit harder to figure out if there needs to be a polynomial term. What I will say is that oftentimes there will be other studies that have done it before that say, hey, it's probably always a good idea to include, the non-transformed and then the polynomial term, right? for whatever, and then all your other predictors. It's a little bit harder just to go in and sort of figure that out on your own. Again, sort of a trial and error situation where sometimes it makes sense to do it biologically, but the case in multiple regression, it's a little tougher to kind of figure out. So I'll just sort of leave it at that because it does kind of get sort of complicated, and I have never really seen many examples of a polynomial term in a multiple regression case, usually because those other variables that you have in there are doing a fairly decent job of explaining the outcome, right? All right, so let's talk about the math, because the reason why we don't go into a lot of the math is for two reasons. The first reason is that you already took Stat 2050, right? And so that sort of covers, all the basic stuff, how to calculate a mean and a median and whatever, in through t-tests, and then a bit into the ANOVA world, and then it stops. And it stops there for a reason. And then this class picks up with all of that, just doing the computer stuff, and then not even really going into the math of how a linear regression equation is formed. There's a few reasons. The first reason is now that we're able to work with really big data sets, right? So doing it by hand is annoying. It would take so long to do, and there would be so many areas where you could make a typo or forget something or make a small mistake that screws everything up, right? The second thing is that this class does not require calculus as a prereq, right? So, many of you have taken calc, which is fine. But in this case, you would need sort of upper level math courses to really understand what's going on. Now, for the nerds who care, and I use that term endearingly, of course, right? But for the people who really enjoy the math, let's talk about it for a little bit. If you don't like math or have not taken up to Calc 3, then skip this. Who cares? I know I don't care. That if you really understand, how the calculus here works. But I'll show you since we're all curious. So here we go. Okay, let me take a sip of coffee here. All right. So we assume that y equals mx plus b, or y equals beta naught plus beta 1 x1 is the way that a line fits, right? We have the intercept, we have the slope, and then our predictor, and then the outcome, right? When we do that, what we're trying to do, or what the computer is trying to do, is we're trying to minimize the distance between the observed point and then the fitted value on the line, right? And we say that that's going to be this, right? We standardize it to be squared, so all of the values are positive, so when we add them up, we don't get any weird zero values or anything like that. We square them and then add them up, right? And that's going to be the assumed vertical distance between the fitted and the observed, theoretically, okay? So we haven't even plotted it yet. We're just saying that theoretically this is the way it should be, okay? So that means that this di squared, right, is our squared regression equation minus the fitted values, right? Okay, so that's good. That's fine. Okay, so what if you recall from calc that when you take the derivative of some function, right, that's a minimum, right? Or when you take, hold on, let me back up a second. When you take the derivative of a function, that's like the instantaneous slope. If you set that to 0, then that's either a minimum or a maximum, depending on what kind of function you're working with, right? Okay. Okay, so what we do here is we take the partial derivative of our s of this di squared with respect to the intercept, okay? And then, that looks like whatever it looks like, not super fun, right? Not super great. And then we set that equal to 0, whatever that is, and then we get the estimated minimized parameter for that parameter, which in this case is the slope, or the intercept, b, and then we do the same thing for the slope here, this m, and then we're pretty much set, right? So the minimized value that we can get is the sum of the fitted minus the slope, and then the sum of the observed divided by the number that we have. And then we see that it's a little bit more complicated for the slope, but it's all there, right? Again, I flew past this. If you want, which many of you might go on to more advanced stat classes, if you take regression and maybe advanced regression, you'll go over this stuff. Again, calc is big time needed for this kind of stuff, and this is why we don't go into the math, right? Because it's many people don't need to take calc up through Calc 3 for their degree. Some of you do, and it's fine. This all might look familiar, might make sense, but for a lot of people it wouldn't, and it's just not necessary to do since we have computers. Okay, cool. That was a lot, but that's that, right? So a little bit of calc, a little bit of algebra here, and we're all set. All right, so welcome back for people who did not listen to the calculus back there. Now we're going to talk about the pairs panels function. I'm taking another sip here. Okay, so I do realize that I kind of like really glazed over this this pairs.panels function. I think I mentioned it once in one video, but plenty of people have asked about it because it is a fairly interesting looking plot. So let's go over it, and then it's useful in many situations. I can't give you all the situations that it would be useful in because it's very widely used. In regression, we're just sort of looking at all of the predictors and making sure that none of them are essentially doing the same thing. That would be looking at highly correlated values or highly correlated variables based on some criteria for the correlation value that you might have. But let's just take a look at it. So I made up these data, totally random, right? Literally random, different distributions. This A here is a normal distribution, B is an exponential, C is a uniform distribution, D is an exponential, E is a Poisson distribution, and then F is another normal distribution. Good Lord. Okay, so what do we see here? Okay, let me erase that. So what is on the diagonal here is just the distribution of that variable, right? So these are all made up random variables of 100 observations, right? With varying parameters and varying characteristics, right? But that's all that middle diagonal is telling you, is the distribution of that variable. Okay. We'll move on. Let's look at this side of the pairs.panels plot here, this correlation matrix. What this is telling you is just the correlation, the Pearson correlation between A and B. And this one is between A and C. See, we sort of do this kind of thing. This one is A and D. This one right here would be C and F, right? So on and so forth. Let me erase all that. So these are just the correlation values, and that's it. They're just the Pearson correlation. Pearson correlations are the default. They sort of encompass the most situations, but you can also do Spearman or Kendall correlations too. Again, we don't really talk about the differences there. Stuff that you should have talked about in Stat 2050, and then also in this case the default is like totally fine. It's a default for a reason in this case. Okay, so these are all the correlation values. We see here that the one that is the most correlated is E and F at negative. Here it is 0.2, right? C and E are the most correlated. I'm pretty sure. Yeah. So the correlation value there is 0.2. Square that, we would get the R squared. Again, this is not regression. We're just looking at the two predictors in this case. This would always be predictors. There are some situations where you might have the outcome on here too, but that just kind of muddles things up. Just looking at the predictors in regression, seeing how correlated they are. That's that. And then the same thing is being said over here, except it's just the points of each, right? So this axis here is for A, right? And this axis here is for B. It plots them, and then it draws the line through them, and that's the correlation kind of thing, right? So these just show you how they behave, more or less. These might be a little bit more useful to copy and paste over than, something on this side, on the left side of the plot here. But it's all telling you the same thing. The right-hand side, the right sort of chunk there, tells you the actual correlation values. And then the left-hand side just tells you what they look like, how they behave. And that's that, okay? That is that. That's the pairs panels. Useful just to do, but not totally necessary all the time. Okay, cool. So those are the biggest questions that I got. There are a few other questions that I did not get to because only one person asked them. So if I didn't get to it, your specific question, let me know. Send me an email or set up a time to meet over Zoom or something, and that'll be that. Now, a few of you asked, what's next? Okay, really great question, which makes me super happy too, that a lot of y'all are digging stats and you want to take some more classes. So Stat 3050 sort of is the introduction into a lot of classes. If you're a stat major, then this is sort of your foot in the door into the sort of core classes, which I'll have up next on the next slide. But there's also some more elective classes that are pretty cool to take too. The biggest thing here, and I didn't write this down, although I maybe should have, but you can look it up too. A lot of the classes, the upper level stat classes, require 2 math stat theory classes. So the first big one is the theory of probability, and then the second theory class is like a statistical. It's actually Stat 3050, but actually all the math that you have to do by hand. There's no computers allowed, which is great. It's so much fun. If you're a very mathy person, they'll be not too bad. If you don't like math, then it might be a bit of a different story for you. I will let you know that I am actually not a huge fan of math. I don't like how sort of it can be intimidating for a lot of people and turn people off from statistics, and you sort of see that in my teaching. But when I took these classes, it is actually not as bad as you think. It's really actually kind of fun, I think. But I'm also slowly sort of realizing that I'm a big nerd. The other thing with this is that these 2 theory classes that are prereqs also have prereqs, and they are up through Calc 3. So Calc 1, 2, and 3 are sort of the requirements there. So with all that being said, what other classes should you take? Well, if you want more of the second semester, or want more of the second half of the semester in 3050, then regression analysis is your class, right? You go into a little bit more advanced regression models. You do more types of transformations and interactions. You make some really complicated models. It's pretty fun, I think. But that's sort of the next step, I think, as far as the second half of the semester goes. If you want more of the first half of the semester, the t-tests and the ANOVA, you can take design and analysis of experiments, where you pretty much just do ANOVA all day, where essentially you just construct and compare a bunch of different designs of research and scientific studies, and you figure out the best way to kind of maximize the amount of findings that you can get. Okay, if you want a little bit of a combination of both of those, you can take applied multivariate analysis, which goes into more advanced forms of regression. So we go over linear regression because it's fairly intuitive. A lot of people can understand it, visually at least. But there's all sorts of other types of regression too. We have Poisson regression, we have logistic regression, we've got just so much ridge regression. We got this crazy world of regression that is seemingly endless. but that class sort of describes them into, or at least puts them into, manageable bins. So doing a bunch of multiple regression, canonical correlation, discriminant analysis, factor analysis, multidimensional scaling, all that kind of stuff. Good Lord. It sounds complicated. It's not that bad. It's just using different tools to describe some outcome. Okay, so those are sort of the core classes there. But if we go on, these are some of my favorite classes that I think are offered here. Spatial statistics is sweet. I think it's super cool. It's sort of what my research revolves around. But it's essentially regression, but just about your front yard. Not really. It's pretty simple. But essentially what it is that you're modeling spatially correlated data. And what it does is pretty interesting, I think. The model that you make, you actually don't really care about what the model says about what's known, but you are actually able to say what is left out. And it might be a function of sort of the land, whatever it may be, right? Which I think is super cool. Because theoretically, you can get to telling the whole story with spatial statistics. So regression, just with a little bit extra. And then, so categorical data analysis. That's awesome. That's a really cool class. It delves a little bit deeper into regression in general. But the biggest difference here is that we don't have a continuous outcome. Y is not some distribution of continuous values. It's actually an outcome, literally like an event. So whether it happens or it doesn't. And that's usually denoted by ones and zeros, which is pretty interesting. So the biggest tool there is logistic regression, but you also get a little bit into Poisson regression and log linear models, sort of telling you the probability or the odds of an event occurring, which I think is super sweet. Cool. Last thing, time series analysis and forecasting. So this whole class that I taught, the Stat 3050, regression, right? We're not allowed to extrapolate beyond the data that we have, right? How about a whole class that just does that? And that's really all you do, right? You work with these really complicated models that I think are super cool. The data is all over the place. It's certainly not, you're not fitting a straight line. You're actually fitting a bunch of bumps and peaks and troughs and all that kind of stuff. And then you're able to sort of predict future values with forecasting based on these models, which pretty crazy. The sort of trade-off there is that you do sort of get into some pretty complicated math and complicated model building. But that's just the class. So, with all of that, that is that. If I didn't answer your question, let me know, and I will. I'll set up a time to meet with you. But again, you killed it. I think you did. Everyone did a really great job this semester. Learning R and learning stats, like this is the real world of stats. A lot of computer programming. Learning R is not easy, and you all really killed it. Even though you might think that you're just copying and pasting, my own code, even then, like filling in the correct stuff and making sure everything works and handling errors and stuff like that, that's a big deal. And I think it's really great that you all have done a really decent job at it. So, with all that, thank you so much for such a great semester. Y'all are great. If you need anything during the semester, let me know. Stat related, not stat related. If you need anything outside of class or outside of the semester, just let me know. I'm here to teach, but I'm also a human too. So if you got anything you need to chat about or anything in general, you just let me know. All right. Y'all stay healthy, stay smart, and I will see ya when I see ya.